Hello everybody and welcome back to our industry session this afternoon. This second half is going to be an industry panel on the topic of defining useful quantum computing. What are the key indicators and when will it happen? So I think it's time to kick off our panel. So first of all, we've obviously heard a bit about the companies that our panelists are from, but I think it's nice also to hear a little bit about the individuals themselves and their backgrounds. So perhaps if you'd just like to take a minute or two to introduce yourselves. Shane, do you want to kick us off?
Sure, yeah, so I'm Shane Mansfield. So my background is computer science. I did my PhD at the University of Oxford in the Department of Computer Science there. Before that, I was like I'm a strange hybrid character because before that I did maths and physics. So it was a strange foray into computer science at that stage. I followed like a very classic academic path for several years. Like various fellowships took me around to labs in the UK and France. And then about 3 years ago, I met with the founders of Quandela. And so at the time, it was a component company that were manufacturing photon emitters. And they were kind of, it was the point at which they were thinking about, do we see our future as that, or do we try for something a little bit more ambitious and go for like actual quantum computing? And so that was an expertise they didn't have at that stage. I started discussing at them just at the right time, so a very nice opportunity for me to come in and be the person to think about what you could actually do with all of this nice technology that was starting to be mature already. So it's been 3 years now. I've been at Quandela building up the theory work and over the overall research and development program there. It's been going very well. So yeah, I guess seen many things in the slides there. So that's my background.
Thank you. So hi, I'm Claire Le Gall. I have actually kind of a similar parkour to you, except for the fact that I stuck to physics. So I did my graduate studies in France, moved to Cambridge for my first postdoc, and stayed in Cambridge on a Royal Society fellowship and set up a group working on developing good solid-state qubits, spins in semiconductor quantum dots, and controlling nuclear spins as well in these systems, and also with an emphasis on networking, so distant entanglement of spin qubits via the photons they emit and things like this. And a year ago, I switched to Microsoft, but before that, I had done some consulting with New Quantum, and actually, after a very nice year at Microsoft, I decided to come back to the field of quantum computing and recently joined New Quantum full-time as VP Quantum. So I'm very, I've recently joined, it's been 3 weeks now, but I have the consulting experience to have this global view of what the company is doing, so I hope I can answer more questions.
So I'm Francesco Battistel. So my background is in physics, theoretical physics, and like my PhD was in particular then about quantum error correction, but also working a lot in collaboration with the superconducting qubit lab. So kind of making like surface code, but studying it and in a way like much towards this kind of experiments. And then I joined Qblox with taking this expertise then in quantum error correction to Qblox, and the job title is Roadmap Leader for Photon and Quantum Computing, which is hell of a title also for us. Like we're still parsing what it means, but like the things are, one is like this thinking about the strategic long-term view of the company and doing like product management and thinking about what kind of products we want and making collaborations or grants and also then participating to conferences and like coming from PhD in science, then just continuing this like also connection with the scientific community.
Hi all, so I'm Stasja with Phasecraft. I have a bachelor's in computer science, after which I worked as a software engineer for about 2 years. After that, I joined the University of Bristol Quantum Engineering CDT, and I got my PhD basically on the quantum information of photons, so entanglement, distinguishability, and similar topics. And after that, I joined Phasecraft, where I've been for the last 4 years. So I'm a senior quantum engineer at Phasecraft, and I'm mostly interested in things like quantum algorithms design, applications, implementations, and so on for NISQ devices.
Great, thank you very much. So just to let you know, we've got some questions that we'll kind of start with, kick the discussion off, but please do be thinking of your own questions. As a reminder, if you're in the overflow room, you can ask your questions by going to the Q&A section on the website or the app. Just to say, if you're standing at the back, there are a few seats around if you'd like to come and sit down. So I think looking at this, perhaps the most important question to answer first is, what do we mean by useful quantum computing? Stasja, would you like to kick us off?
Yeah, sure. Well, I guess I'm fairly biased considering the company I work at. But I'd like to think that once we can do kind of an interesting problem that hasn't been engineered for whether it's a NISQ device or fault tolerant, but something that's kind of independently interesting, let's say, and we can do that on a quantum device, that would be kind of the point at which I would say, yeah, okay, we're doing something that's actually useful for the kind of a more global community, not just scientifically interesting for the quantum community.
Would anyone like to add anything to that? Francesco, go ahead.
Yeah. So, well, okay. I think that maybe we're not so close to the applications, but I would like to say two things. One is that I mean, I hope that the applications are also going to be useful not just for big corporations, because I mean that's so far what like. I mean that's mostly like if we need like a lot of money to run a quantum computer, then it's probably some big corporation that then has also some specific interest in some of these big problems, but hopefully then there is also something else. And the other angle I wanted to bring up was that I wasn't buying some things that I was hearing about, like that maybe we can be also satisfied initially if we're not necessarily super fast with a quantum computer, but if we can like solve problems that we can already solve, but with less like energy required. And then I spoke with some HPC folks for which actually the energy consumption matters a lot. And then I thought, okay, maybe then there is also some value just in saving some power. Yeah.
Claire, do you have anything you'd like to add?
Thanks. I like your second point, though as an experimentalist, I struggle to see how we would use less energy so far. But let's hope we get there one day. Yeah, I mean, what to add? You guys have said it all, right? We want to solve a real life problem, a practical real life problem, and I think that will be the tipping point from a conceptual point of view. And I think from a hardware point of view, we'll have this once we have truly developed modular architectures that are scalable. And I think that's why in a lot of the talks you heard about today, people are really taking this approach, synchronizing elementary FPGA units or building racks with replaceable modules. And I think that's really what we're focusing on at the hardware level.
Shane, please go ahead.
Yeah, so maybe I have a slightly alternative take on this one. Like, so I would say for useful quantum computing, it's it's like you have to do something that you couldn't do otherwise, that you can't do with classical technologies, right? So that's kind of a given. Otherwise, you just do it with classical technologies. And then, okay, yeah, sure, it should be something that's like industry relevant. So actually, if you're very practical about that, industry relevant means someone wants to come along and actually going to put money into it and get money out of it, probably. So sometimes as scientists, we don't like to think that way, but I think that's probably when we're going to say it's practically useful. But then if it's just about doing something that's not available to classical technologies, I mean, we can think about that in, like, I think we need to think about that in a slightly flexible way. So there are already some things that we can do with quantum technologies that we can't do with classical technologies. So things like violating Bell inequalities. All right, so that got Nobel Prize this year, and that's definitely something that you can't do. And then can't do, right? That's also something you have to be careful about. So I can simulate what a Bell inequality experiment is going to do on my computer. So then we started to talk about something that's not just raw computational power. So for Bell inequality, I can't do it with classical technologies, which have comparable constraints, right? I can't do it with like distributed non-communicating systems. And so here we start to think a little bit outside of the box, but there's already something today that has practical relevance, that is useful quantum computing maybe to come from Bell inequalities. And so I would argue that certification is perhaps a first application that we could think about that is useful. So something that I was very excited about working on this year was our work on certified random numbers, which we do by Bell inequality violations. And so I think, I mean, if we think about what can be useful, I would argue that that's something that's already useful. Someone would say to me, okay, but it's not like raw computational power. Fair enough. But still, I think it has applications. We can think about certification going a little bit further as well. You know, we can talk about like secure delegated computing. It might just be classical computing, but you might get security that you don't have available to you with classical technologies. And there's a lot of interesting work going on in that direction. And I'd make another point, which I think gets lost sometimes. It's about people focus a lot on raw computational power. They look for like an exponential separation or something like this. Actually, what's going to end up being practical, I feel, for people in industry is not when they get like a huge exponential separation. It could just be like a factor in something. It could be something much more modest. Also, we're used to thinking in quantum computing about, you know, the big picture. It's been researched for a long time, and we all start writing our grants, and we start by saying, well, you know, when we have these large-scale quantum computers, we're able to do things we could never even imagine, you know, problems that we can't even access today. You're in a whole new computational regime. But it could be something different as well, right? It could be just attacking a problem that we can very well solve today, but it just takes incredible resources. So maybe we could just do it more efficiently with less quantum resources. And I mean, this seems difficult. So if you look at, you know, the massive dilution fridges and so on that some people are working with, but this is not impossible. And I think that's a very important line to have in mind and to follow up on.
Sorry, if we may have a little bit of disagreement, I think you've just lifted like a very a splitting issue between the community about the value of exponential versus non-exponential speed up. I think it's fair to say to this audience that, you know, not everyone agrees on that front, because quantum computers seem to be inherently slower. Sorry. So if they are slow, it seems that you know, having a less than exponential speed up in your computation down the line will not allow you to arrive at useful computing power, but yeah, or useful computation.
So I would say, if you talk to people in industry, they just care about getting a factor 2 sometimes. This can have like a dramatic effect on what they're doing if they're working with like a distribution network or something like this. Just a very modest factor. But okay, I take the point about the exponential thing. Okay, maybe we brought up like a subject that can cause a bit of debate. But okay, let me roll with it. So I'll just say, you know, one thing. Maybe you are getting an exponential advantage, but maybe it's not an exponential advantage that's taking you into the realm of solving problems that were never before accessible. So I'm thinking, I have something concrete in mind. It's kind of this idea of energetic advantage that's been proposed by Alexei Ofev, for example. I think this is something that people need to pursue actively. It's an idea that's out there that, the ball is there, someone needs to pick it up and run with it now, maybe. But I think there is something very exciting about the possibility of maybe doing the same problem, but just putting less resources into it. And it might be off the back of an exponential separation, but it might come before you get, a raw sort of advantage in terms of computational power.
If I can have a shameless plug as well. So actually, one of the projects we work on is so on the QA kind of side, the optimization side, the constraint satisfaction problems, and that's exactly where we're looking. Like we're looking at it's still exponential scaling, but it's better exponential scaling when it comes on the quantum side of things. So in practical terms, that makes a difference when you're looking at these problems. So I agree with that. I think. The problem of where that useful kind of boundary happens is there's still the flip side of we still need the right fidelities, we need the right hardware to, we might have that exponential separation, we might be able to do something algorithm-wise, but we also need to have a device that we can still run those algorithms on and so on. But yeah, I would say that's for me, that's legitimate, practical application that would be of interest. Yeah.
So, yeah, I guess talked a little bit about maybe different kinds of useful quantum computation there, and maybe what we mean by useful, both in terms of application and kind of meaning. Those large-scale calculations and computations are clearly some distance off. What kind of indicators or markers do you think we might see along the way that some of these applications or improvements might be possible at some time scale? What are the kind of key markers and indicators that we're making good progress towards these possible directions? Don't know if anyone wants to kick off there.
Shall I? For me, again, I'm an experimentalist. But it's if we see that when we scale the system size, we scale computational power. For me, this is the signature that we are on the right path.
Maybe something maybe a bit more generally. I think that looking at the evolution of the classical systems, I think there were two turning points, and one was, I guess, the transistor, and so that's a bit of the search for a good qubit. It seems unlikely that we can have a qubit that has so low error rates to be comparable with a transistor, but I mean at least some qubits that probably need 1 or 2 order of magnitude lower error rates than now, and then some good error correction scheme on top. And I think that then in the classical domain, the other big turning point was with the integrated circuits, because then we talk often a lot of the overhead we have in quantum, and there's a fear of also more qubits, but often the problem is not making more qubits on the chip; it's to control them, and integrated circuits. What happens in our modern processors is that you have billions of transistors, but you don't have billions of control lines, whereas now we need 4 control lines per qubit. So if we have 1 million qubits, it's 4 million control lines, and that's where really the problem is coming from. And so I don't know exactly what's the way to solve this. There is a lot of multiplexing in space and time in the classical domain, so that you can just use a few hundreds of lines. But I think that's something that needs to come from both the chip side and the qubit design, and then on the control side that we can do some sort of quantum integrated circuit. Yeah, and then just to add one more thing, which is like almost half a joke. Like, I mean, for Qblox, we have this rack-mountable control electronics now, and then so it's this kind of standardized thing. You just have your rack, you put a lot of those. So maybe we need, like, also for quantum computers, that like a big turning point is we have rack-mountable quantum computers, and then that means we have already solved a lot of issues about scalability fundamentally. Yeah.
So I think one thing, like we're all aiming for whatever this is that we can agree on at some point, the definition of useful quantum computing, and maybe that's where we're aiming for. But okay, so as indicators along the way, I think one step, which now that I start to like have this kind of dual role of somewhere in between theory and experiment sometimes, something I think is very important is to kind of get this feedback loop going, of actually having a full system running, of having the software talking to the hardware, and having the algorithms people really working with the hardware and engaging with the problems that are there, understanding how they can improve it. The hardware people also learning how to improve the hardware and as a function of the algorithms. So I think this kind of feedback loop is very important, and it's probably at the moment that we're starting to see this happening in various places. And that doesn't mean every company has to do all of it by themselves. Of course, this can be in combination, but I think so I have seen in my own experience now, in having gone from conceiving some algorithms, implementing it, and going through the actual runs, and you learn a lot when you actually implement things. And I think by doing that, we will really greatly accelerate this whole endeavor. And I think also making the tools available like that to people, talked about making things available on the cloud on our side. Many people are making things available on the cloud. I think this is very important to open up the tools that people play with them. It's when you play with them that things start to happen. And and we shouldn't fool ourselves that everything is like in place already. It's not. Probably like the killer app. It could very well be something that nobody has even thought about yet. So like opening it up to the master's programs and to the students to play with is, I think that's really important. So I would say that's a really important step. Maybe another thing, like kind of on a slightly different line, just to talk about like an indicator that things are moving forwards. I could also say, like, on a more sort of like for personal stories, I've been working in quantum computing on some level since 2009. So yeah, there'll be some other people younger than me in the room maybe, but I think already in that time can see like a huge change. So there is something very tangible about the pace of progress and the pace of development and what's coming out. And I noticed this recently when I talked with a colleague who did his PhD with me and then moved out of quantum computing. So he's working elsewhere now. And I met up with him in London not too long ago. I mean, maybe after COVID. And I was talking about some of the things that happened, and I was like amazed that all of these things that were already starting to seem like far in the distance to me, he had never even heard of them. So like we talk now a lot about NISQ algorithms, this whole area of variational algorithms. This had completely passed him by, and he only left in 2015. Or maybe he started to see the beginnings of some of them, or the quantum advantage experiments. And okay, yes, we can dispute whether you can classically spoof some of these or not, but the point is there. So I think there's definitely like a tangible acceleration, and that probably comes with putting more resources into the field as well.
Are there any kind of key challenges you think the industry needs to overcome? Is there anything that keeps you up at night worrying about how we'll get to this large-scale useful quantum computation?
Maybe I'll start on that one. Many things keep me up at night, I guess. I think maybe one I would bring up is, and this probably comes with the whole expansion of the field that Shane was pointing out. and that's we're kind of getting a lot of funding, a lot of interest. There's a lot more engagement and things like that, but we're kind of struggling for staff. Like just generally finding enough people that are kind of qualified in the right areas, trained in the right areas. There's still kind of a relatively high threshold for getting into the field where like often you have to have a PhD and so on. And like I would say that's kind of a major challenge, at least for us.
Just to comment one thing about the staff and also about the previous thing about the beer and the, and the free holidays. I mean, okay, that makes it sound like I think that in the industry world, especially for startups, I mean, yes, there is some maybe shortage of talent, but like what was more important, I think, for startups is like collaboration than competition and like. I think but I think every startup is involved in a lot of these kind of collaborations to try to work together. And then also to answer then also on my side the question. First I wanted to say that I'm aware that about the power that you said that experimentally it's an issue, and like the point is that. Like with our technology, but like similarly across the competition, like controlling 20 qubits is about 1 kilowatt of power. So if we need then 1,000 qubits, we already go to megawatt power, and 1 million qubits is gigawatt power, which is just starts to become a bit insane. And so there's definitely a lot of work that needs to happen so that we can scale down the power that is needed to run these big systems, and I mean also in the end it's also related to money and also like the cost per qubit of every part of the stacks, not just the control stack, but cabling, fridge, like it all has to scale down because otherwise, like labs can afford a few millions now to build a few tens of qubit stacks, but you cannot multiply that by another million factor and make it feasible. And then another challenge, another of the key challenges that I think sometimes about is when scaling up, if we then need quantum error correction, if we then need to do magic state injection, then we need a lot of these magic state factories, and I come more from superconducting qubits where the qubits are a bit like they're stiff in place. Maybe for other technologies, other people can comment, but it's not clear to me like okay, where are we going to put all of these qubits that do the magic state distillation on chip, and how are we going to then route these magic states when they are ready and without degrading them too much in fidelity and bringing them where they are needed to do the T-gate.
I fully agree with what Francesco just said. I think these are exactly the things that keep me up at night. So, which boil down to how do we scale up, and how do we reduce our energy and space requirements, simply space requirements as well, to have millions of qubits. And why does this all keep me up? Of course, it's, we need to bridge the gap somehow between how many qubits we need for useful quantum computing and how many we can have in the lab. And I really hope as well theorists make some crazy breakthroughs. As an experimentalist, that's what I hope.
I'm going to be smug on the scaling up thing as a photonics person, because I feel like the energy required to scale up is maybe less of a concern on our side. So I mean, for fixed kind of hardware size, you can generate, say, as many as you want, but you can really generate a lot of photonic qubits with that. So maybe that's not the one. But I take the point. I think maybe the theme I see through it is kind of the sustainability of the whole project. And this is like a big one, getting like enough good talents and good people. So this is something that, okay, this was also a big struggle on my side. It's something that definitely caused me to stay awake at night sometimes. I think in France I start to see that you have a lot of master's programs are opening up now. The bottleneck is further along actually at this stage. So there still is a bottleneck, and it's now we lack people to supervise PhDs actually. You know, and we have to be very careful about that because I was like mentioning in conversation earlier as well, you know, there's like, it's happened before, there's a danger of overfishing the waters sometimes, which I think probably happened in error correction. I think so many top error correction people got like lured into, you know, the big companies that there was no one left to actually supervise the next generation of students. And then, so that's a danger. Should watch out for that. And, but yeah, I mean, maybe to echo what you said as well, I think, so yeah, we can pray the theorists do everything, but no, but seriously,
No.
seriously, I'm joking. No, but I mean, kind of joking. But no, but seriously, there's a point behind that. I think is very important to balance the short term and the long term. And so, you know, now that we start to see the transition into industry, there's something that's really good. You know, there's this kind of impatience. We've got to get it working. We've got to get it solving real world problems, and that's great. That's like really important, and that's a good driver. We have to be careful not to like separate the truck and the trailer kind of thing. You know, like we also need to continue doing this fundamental research. The academics need to, you know, keep doing this work as well. You know, they need to have this longer term perspective. Because, you know, like I was saying earlier, it could be that like the actual killer app, the one that like the thing that's first to come online, it's something that we just haven't thought of yet. Or, you know, I'll go even a step further. I would say like I give you a large scale fault tolerance quantum computer today, and then just what are you going to do with it? And someone's going to say to me, I'll solve Shor's algorithm, and then that would be fantastic. Like that would be great. You get an amazing paper out of it, and it'd be like a huge milestone, like bigger than, you know, the quantum advantage experiments and so on. But like, is it going to like really upturn industry, change the world, all of this stuff? You probably crack some like old you know, stuff that was encoded that people have stored away somewhere, but like what else are you going to do with it? So you know, people need to be working on this. Like now is the time for that. And so we need to also have this kind of long-term, more kind of cathedral building sort of thinking that we shouldn't lose. So yeah, maybe if that's one thing, it's kind of, I mean, it's the thread maybe that goes through all the responses, kind of the sustainability. And I think a part of that is keeping the long-term and the short-term perspectives a bit balanced.
So thinking about those challenges, perhaps both on the recruitment and the technical side, is there anything you would like industry or academia to do differently? Anything you think that could, kind of accelerate tackling any of those challenges? Too difficult a question.
I don't know. We already touched a bit in this workforce education, and I share some hope that then when like some intermediate size, I don't know, quantum computer becomes available, that then people are trying out things and that they discover something. I mean, I'm just thinking that I think in classical computing, a lot of the algorithms that have been used maybe even for a bunch of time and that they were successful, they didn't necessarily come with a proof that they were always polynomial in time and that the worst case was not exponential. But there were a lot of heuristics that people tried, and then something works, and then even if it doesn't work always, it can be already be beneficial.
I think as well as on the kind of the recruitment side, like I mean some of the points that have already been brought up, like kind of handle some of those challenges, like so whether that's collaborations, like collaborations can help, and when Shane was mentioning about kind of making sure that there's that balance, short term, long term. More training, and it's great to hear that in France there's more programs. Like hopefully we'll have even more in UK as well. So so like for example in UK we have like 2 CDTs that are quantum focused CDTs, and that's about 20 people that comes out a year out of that. That I don't think that's enough. And then, you know, like, there are other options, I guess, which is retraining people, and just maybe like a larger engagement from industry and companies that aren't specifically focused on quantum still or yet. Because a lot of the times we see that there are problems that we don't quite understand what they are, or that we should even be looking at them because we're not experts on that. We're experts on quantum computing. And this is why I think some of the government grants where you do get connected to these kind of end users are amazing, because they come and tell you, well, actually, you're focusing on a completely different set of problems than you thought you should be. And these kind of engagements, I think, help because they make sure that the staff is not overloaded with the problems that they shouldn't even be focusing on. So, yeah, that's maybe another way.
So touching on what Stasja just said there, and also what Shane was mentioning, in terms of, yeah, what are the real end applications? What would we do when we have a large-scale, accurate quantum computer? How far can we answer that question yet? Do we, and what can we do to get to those answers?
I feel like I'm being picked up. I guess maybe Phasecraft perspective, like the stuff that we've been focusing on for the past few years, is a lot of this kind of materials simulations, whether that's battery materials that I talked about a little bit during the presentation. Photovoltaics is another one that we're looking at, and you can kind of see how this might happen using maybe variational quantum eigensolver. Where you're looking at a specific material, running it through the variation quantum eigensolver multiple times for different charges, and you know you could come up with an idea of how that could work. I think, and then the other one that we've been looking at is the one I've also mentioned again earlier, which is the optimization. Yeah, it's a hard question. If we knew the answer, we probably wouldn't be having this conversation right now.
And I'm sorry, I'm going to ask probably the hardest question, but you can all feel free to not answer very precisely. How well can we put a timeline on anything going towards useful quantum computing? I hate being asked that question. So
I think we still need to settle the definition of it.
True.
Well, first I want to add we're talking a lot about quantum computing because obviously that's the sort of the most interesting, but like quantum technology is also quantum sensing, which I think is extremely underhyped, and like there is already something, and it's probably here to stay, and it will probably grow, and so yeah, it's not as maybe exciting as the computing part. And then you also have the communication, where I mean, like if you lose computing, you lose a lot of the applications that are about distributed quantum computing, obviously. But then yeah, I think that I mean QKD is already a bit here, and that can also be valuable, I think. But then in terms of timeline, I'm just gonna say that I mean, like if you are a good, if you want to make a good guess, now you can make a lot of thoughts and pull in through your computation a lot of factors, and then you get to a certain number of years. But then, like if you're a really good planner, then you just take that number and multiply it by 2, and that's probably what's more close to reality. So yeah. It's tricky though to quote a number. Then I'm gonna be quoted for that number. But I think it's just gonna take some time, and it's important that we don't overhype the field too much, and that because the field needs, I think, for many years, like a continuous stream of funding that shouldn't just dry out or not. At some point, like there's. I mean, there's a lot of work that is happening in parallel now because there's a lot of funding, but there's also some degree in which you cannot parallelize too much, and certain scientific discoveries or development, they need to happen sequentially. Yeah, so it's gonna be important to give that space and time.
Particularly when the workforce is fixed. There are bottlenecks, as we said, but infinite amount of challenges on the technical and theoretical side and hardware.
So I'm inclined to say that like some useful quantum computing is already here.
You're
So
the
I put myself
optimist.
down. Maybe slightly. I don't know. I think we all have like an optimist and a pessimist in us. It's important to like play with the tension between the two of them. That's fundamental for a scientist. But no, I will point to something. I would say like something that I'm really proud of and very excited by in the last year is that we actually succeeded in doing some certified random number generation, and it's a thing that you cannot do classically. So okay, it's only a 2-qubit processor, but here's an actual advantage. You know, it's an application, so not computational power again, but an actual advantage today that people are willing to buy and use, and so you know, to some extent, it depends on your definition of useful. But I think for my definition anyway, that one works. And then okay, so yeah, like I won't go putting a date. Like nobody wants to do that. It's a bit mad, but you know, we can say some things for sure, and we shouldn't be shy to say them. Like one thing is that we're kind of entering this quantum advantage era now. So maybe there's some debate about the experiments that went, the quantum computational advantage experiments that went, and some people will still be claiming that, okay, we can catch up and we can spoof the results and so on. But you know, I think in principle, nobody or very few people like actually doubt this anymore, that you know, it's anything more than a question of just adding a qubit or a few photons. And so that's quite interesting. You know, that's something that I noticed myself when when I first started engaging with photonics. You start doing the calculations. It's this incredible thing. You know, you work with like a really simple system. You put your photons into like a generic beam splitter, and you just try to like calculate where they're going to come out, and you end up, you know, you get this boson sampling type thing. And basically, like once you get to, we're doing like some calculations. Like once you get to like 20 photons in 20 modes interacting, like that's beyond what like classical supercomputers can handle. That's so, I mean, that's the ideal case. Okay, we're not dealing with noise and spoofing strategies, but like that's already quite remarkable. That's like not a huge quantum system, and that's already in the regime where you can be doing interesting things. We also did like a back of the envelope calculation when all this GPT-3 stuff was coming out. Like at about 24 photons, was it 20 photons? I don't know. It's like again around this range, like 19, 20, something around this. In, you know, some similar number of modes, you end up with like basically a number of states accessible. You're working in a state space that's like comparable to the state space that they have behind this GPT-3 model. Like not at all saying that's as powerful as it or anything like it, right? So don't get me wrong, but just you know, it's there's some quite remarkable things. Like so I think it's important to say that we are going into this regime, and once you're in this regime and you have the tools and you make them available, you're playing with them, I think you're in the realm where things can happen. So that's not okay, that's not putting a precise date on something, but it's saying that, well, I think we have like crossed some milestone recently. And it's an exciting place to be, and yes, something could crop up anytime now, if we're optimistic about it. Which I want to be.
Just to say, we have reached the end of the scheduled time, but I think as we were delayed from before, if that's okay with our speakers, we'll carry on for a little bit, in which case I think we'll open up questions to the floor. As a reminder, if you are in the overflow room, use the Q&A section on the website to ask a question. So, would anybody like to ask a question? Oh, there's one on the balcony.
I just wanted to go back to Shane's point, I think it was, about kind of the feedback loop between hardware and software. And I think at the moment a lot of software is done kind of agnostic of QPUs, so you kind of have this division between people who are doing software and they're working in terms of sort of arbitrary gates. But we're seeing more and more that like a lot of SDKs are offering things like pulse level control. Do you think the onus needs to be on software developers to start working at a kind of lower level, or on compilers, optimizers to kind of better translate these arbitrary circuits into like native control?
Should I? Yeah, I'm not sure who the onus should be on here. I just think it's important that someone is doing it, and that. Yeah, I think it's important to actually try running things, to actually like try getting numbers, even if you're running things that you know to be classically simulable. But it's like just once you get that chain going, you start to think about where can I start to optimize, and there are an awful lot of things to play with typically. Yeah, so it's like yeah, you start to realize just how complex of a system you're playing with, and okay, it's going to be different with every hardware, but I think it's important that people like think the full way through to implementing things, whatever the hardware they choose to be. I think we'll see more acceleration, more advances when that happens. Yeah. So yeah, I don't know who the onus should be on, but we should all make an effort.
We have a question from the overflow room. So does your company consider the ethical considerations of rolling out quantum technology? For example, quantifying the environmental cost of running full-scale fault-tolerant quantum algorithms, or in a scenario where a state government requests your technology to run simulations or implement cryptographic protocols?
I mean, before I mentioned that we should reduce power, because I think that, yeah, indeed, it's not, if we need millions of qubits, I mean, it depends a bit, I guess, on the technology, but yeah, it's not affordable to have, to require a nuclear power plant. I mean, I like nuclear power plants, but just to talk about the scale of energy, like, or a bunch of coal. Yeah, mining a bunch of coal is not a good solution to run quantum computing, I think.
About the who will be the end user and what for, I think actually as a physicist, I have the inner conviction that what will come out of a full-scale error-corrected quantum computer will also impact material science, as we have explained, and that, you know, people think about Shor's algorithm and the ability of suddenly hacking state secrets, but I think that this in practice will be probably the last to arrive on the table as an application. It's the one that is out of reach, the hardest to achieve, right? So I'm sure that before then we will have actually applications that have a real societal advantage and impact. Good impact.
I suppose, like with every technology, you have these possibilities for, you know, positive, negative uses to come out of it. I don't know how it is. I can't speak for all the companies. I can't even speak for everyone in Quandela, but I can say these are conversations that we have. Of course, everyone has them. Something that we're very interested by, where we think like there's a lot of scope to do some important work in the coming years, is the energy question, actually. And so I'll plug again this kind of quantum energy initiative launched by Alexei Ofev and others, which I think is really nice approach to looking at the sort of trade-offs that you can have. I think it's very important for not doing things too wastefully and irresponsibly. And I think we all need to put some effort into this. It's definitely something that that we are taking quite seriously. That's one of our projects on the horizon at Quandela as well, to start doing this energy budgeting.
Yeah, and the question also had this part about cybersecurity, which I don't know, like in which sense it was meant, because it could also be meant like that the quantum internet and the quantum computer should be secure under malignant threats. Because I think that the classical internet could have been built in a different way that would have been much more secure from the start, but that has led to a lot of issues that we still have nowadays. And for the quantum internet, I see that people are a bit more concerned, probably because one of the major claims is this is secure based by laws of physics and so on, and then you don't want that actually somebody hacks the whatever measurement device you're using inside your lab. So I hope that there will be that it will continue to be then a concern to make it secure from the architectural level from the start.
Any more questions?
I was just wondering, what are some key theory breakthroughs that you would love to see that might help to shorten this roadmap?
Shall I speak? So we have about 60 qubits with 2% error. Can we have something useful with this? Then we won't be worried about energy consumption. And no, it's. I think everyone we're hoping to make improvements, massive improvements in the error correction overheads and in the algorithms.
Okay, I could add another thing to the wish list, like a theorist wish list. I would love to see better understanding of where quantum advantage comes from. I think we've. Honestly,
Go back to academia.
Yeah. Well, see, this is where I came from, right? So that's my research to begin with.
Full circle.
No, but genuinely, I think it's there are very few areas where we're as close to the bleeding edge of very fundamental research. Really some sort of breakthrough, very fundamental quantum computing theory can have profound impact for the whole field. And I think that's one of them, right? So there's a thing that many people may have noticed if they've been looking around at the zoo of quantum algorithms and stuff, and sometimes it gets talked about, is that you don't have this incredible diversity of different applications and algorithms. And what you tend to have are a few families that follow structurally similar kind of setups. You have the same gadgets being used and so on. So, I mean, there's some remarkable things in there, of course, but you don't have the same flourishing of different algorithms that you do in the classical world. And I think part of that is because we don't have a good intuition for how to come up with, how to write a quantum algorithm with advantage built into it. So in classical computing, we train people to work with heuristics. They're things that you just it gets hammered into people's minds, just by going over and over again. Things like divide and conquer. When you have a problem, divide it into things that I know how to do and whatever. You have all of these heuristics that you just build up in your kind of toolkit. And when it comes to quantum computing, best we can do is okay, well, I know this kind of hidden subgroup problem can be interesting, or I know quantum Fourier transform can be interesting, and it's not much more than that. And I feel like great advance can come from better understanding what the source of quantum advantage is. And easy answers are not good enough. So people will say, oh, it's superposition. This I don't. Or they'll say it's, massive parallelism or entanglement. Yeah, okay, right, okay, fine. But it needs to be something more than this. And so, all right. I could talk about my own pet theories about that, but I won't indulge myself. But I think there's definitely some work to be done there. I think once we could identify that, you could start to use that as your heuristic. You start to build algorithms around that. So yeah, that's my wish list.
Another question here.
So you mentioned that there is a bottleneck because of the lack of workforce. And do you think building a community, for example, with open source projects, would benefit the development of quantum computing? Or how much impact do you think it would play in the development of this technology?
Is that like open source, like software or like hardware?
Yes. Yeah.
Software.
Both.
Both. Yeah. Okay. Yeah. I mean, I think that. Well, I mean, IBM, Qiskit, like if you want to use the bigger chips, you need to pay. So it's not really open source. But at the lower end, it is like that, and that I think has helped a lot. There's so many papers that are based on that, and you can just access and try out things. So I think there is a lot of value in this kind of projects, and yeah, also in terms of software, I guess I'm not very much of an expert there.
The question is, can this be a model for startups? Unfortunately, I think not. I think IBM and Google can afford this. We cannot. It doesn't mean we wouldn't like it.
Yeah, I guess it could be part of the contribution or something, but like it's not, I guess it's not very feasible for startups to kind of base themselves around that.
But it's definitely a great idea. I'm sure, I mean, there are people who are self-taught in programming thanks to Qiskit.
I think also it's probably worth kind of mentioning that the quantum community just generally is quite collaborative anyways. It's quite open anyways. There's a lot of really great collaborations. People don't tend to kind of, obviously there is some proprietary research and so on, but like people tend to want to collaborate even cross companies, not just academically and so on. So I'm not sure open source would be kind of the solution for that problem beyond like some amount of education.
Thank you.
Did you want
to? I mean, we have open sourced some of our software, so like at some level, it probably can be done. That's not to say that there won't are not like proprietary aspects or things that you can add onto it, but I think, yeah, well, okay, so that's a good observation. There is kind of a community spirit already, and sometimes people, when they come to me, like people from academia, and they ask, what's it like working in a company now? They kind of have this idea that, it's like everything's closed and everything's secrets. And I mean, okay, yeah, maybe like some projects or some aspects, but actually there's quite a spirit of collaboration, and there needs to be at this stage. There's so much to develop yet. There needs to be. And usually what I see is that when it makes sense to collaborate with someone, an academic or someone from another startup, there's a way to do that. And if it makes sense, you still go ahead and do it. And I think the community thinking is, I think it's very important. I think it's important also for like companies to actually make their tools available like this. This is a thing I feel like a stock record because I'm repeating it, but it's something that's like very much in my thinking and our thinking, I guess, at Quandela, when we try to like make the cloud available or make the software available, it's important to build up a community of users because, well, they might come up with the next great algorithm that works well for that system, and we get some really interesting feedback from users of our software, actually. And we see people using it for things that we never, thought it would be used for. We thought actually originally that when we put out the software, it would be used by theorists to play around for algorithms. And then it was actually very satisfying to see that a whole bunch of experimental groups started using it now. They're using it to validate their experiments, to say, okay, it matches the simulations that we can run with Percival or something like this. I think that's very interesting. I think basically, I mean, it's a theme that maybe I repeat. Like I think making the tools available, it comes back to multifold, that you reap the benefits from that. So, I mean, yeah, obviously there are limits. It's some things. So I feel, I think we're going in the same direction there.
Yeah, I can also add that I mean, also like not at the level of the software for the algorithms, but we have this software that at Qblox that is also open source that takes it from when you have your circuit to running the experiment. and also the assembly language of our electronics is also like what's running underneath on the FPGA is not open source, but one can program in that assembly language, which is not a common thing, and that's something we do because then like the users at the moment of quantum computing, since it's so early stage, are people that are very deep into it, very expert on it. And in particular for us, then it's sort of experimentally, they're actually running things. And so they have, maybe they have their own software, and they really want to like have this, like they're sort of all power users that really want to use all the possibilities. And then if it's open and it's available, then they can. Otherwise, they would have a wall and they need to deal with what's provided by us. And I think also our users are appreciating that.
Are there any more questions for our panelists? Oh, there's one at the back.
So I'm more from an engineering perspective. So I'm very far end user. All the engineers ask me, what can we do with it? And I have two short questions. First of all, Sean, you mentioned you were hoping for more education in a toolbox how to develop software. And I'm wondering, trying desperately to develop any kind of software helping engineering problems, what would be in that toolkit? How is there any kind of toolkit making it intuitively to generate any kind of useful software? And also, just from a hardware perspective, the main example always is we could use or solve optimization problems, and all of you, I assume, are having universal quantum computers. But as far as I know, there are also annealers. I'm not an expert, I've got no clue. So why should we focus on the hardware you're working on? That's what I ask.
First, let's say amongst the hardware that we are working on, there are massive differences already. There is just an incredible variety. What the common theme is compared to annealing is the belief that we need precise control and entanglement in our machines to make them useful. And it boils down to where does the quantum computing power comes from? And I think if you believe that it's entanglement, and it's a evidence-based belief, I would say, then those are the ways that you pursue.
So the thing about the toolkit, so I mean there are a lot of like great pedagogical materials out there. Like was mentioned, that I think through Qiskit, like lots of people have come to quantum computing not from a physics background at all, like just people who are just kind of curious, maybe people who like playing around with computers, know some programming languages. That's an excellent resource,
But isn't it still the limited amount of algorithms we have there? Like you said, the Quantum Zoo has like 200 algorithms listed, and that's it. But engineers come around the corner and have their very specific problem, and they're like, could you boost it, please? And I'm like, well.
Yeah, so I don't know if there's like a one-size-fits-all answer to that. So like when I mentioned about the toolkits that that came about, that we're developing. So that came about like based on what we were observing, talking to people. So you go to talk to someone and they're like, they have this crazy problem, how to distribute their loaves of bread or something, like, I don't know, whatever, like, and everyone has like their own very specific problem, and then you have to work with them a little bit to break it down into, well, how do I mathematically formulate that? What's the right way to set up the problem? And then you look and you see, do I have some algorithms that work that could actually be appropriate to it? And so that's kind of the beginning of why we started to try to make, just like a standardized set of algorithms available that people could start to go to them themselves and start to wonder, like if distributing the loaves of bread came down to just like solving a graph problem, finding the shortest path or something, then if you have a shortest path algorithm, then you just go straight to that, and maybe you don't need to understand all the details of like the inner workings of the quantum computer behind it and so on. So I think that can be useful depending on the audience, because you'll always get some people who want to dive deeper, like, and really go into the algorithm itself and start tweaking the algorithm and playing with it. So it's kind of different approaches for different audiences. But I think that was a decision we made based on experience of interacting with people kind of from non-quantum, but kind of quantum curious industry, that this was a useful way to go for us, for example, yeah.
So you're using the potential of the existing quantum zoo and just squeeze it into your problem that it fits nicely. So you're not developing some random new software, because this is something I found super hard, like I'm so lost. But using algorithms that exist, of course, just...
Yeah, so I think about...
So maybe if I can just pick up on something, because it kind of relates also to the question that was kind of asked earlier, which is the problem stands at the fact that if you want to be doing something very interesting and very useful, you are like tweaking it to the minute detail on the hardware, right? So you need to have the experience of that hardware platform, you need to have the experience of that algorithm and so on. Then kind of the other side of the thing is like if you're trying to learn about it and then you have the toolkits such as Qiskit, a lot of the research that comes out often has, like if there was code developed, often will have the code that went with that research, that went with those papers. It has it available open source. So it maybe relates back to the whole open source question as well. So, for example, the thing that we did on Google's Sycamore device, you can find that online on Git, and a lot of collaborations with Google that have been done through Circ. So this is not it's their platform; it's not Qiskit anymore, right? You will find it over there. So I think these different hardware platforms often have a way of kind of backing up that, but highly technical research, right? And I guess maybe your question is, where is the intermediate scale? And I think the answer is there isn't one. And it kind of relates back to the whole staffing problem, because now you have to kind of dedicate the staff that turns this into something that's more parsable and something that's more general. So yeah, multiple problems there, I think. And I should say there are like other platforms than Qiskit that do have like really good programs like that do teach in this. I think Black Opal from Penny Lane. I think it's Black Opal. Yeah, I'm not sure, but yeah, like there's a few different options if you're interested. Yeah.
There isn't real life engineering around just yet. Anyway. Right, so that's why I guess maybe the dialogue is not fully there, though you know obviously some companies are you guys are trying already to cater for some needs. But yeah, it's but it will grow. It will happen. Let's grow our system size first.
I think that is perhaps a good place to stop. So with that, thank you very much to our panelists, to our speakers, and also to our sponsors as a whole.